And our next speaker is Hao-Yun Su. He's there. So I hope I got this correctly. He is currently a master thesis student at Siemens, right? That's
yes,
correct.
That's
okay.
Correct.
And he is working on QS, and he will now present to us the evaluation of methods for prediction and computation of the delay violation probability in industrial URLLC applications. Thank you.
Thank you. Okay. So good afternoon, everyone. I am Hao-Yun, and as the nice introduction, I'm currently a master's student at the Technical University of Munich, and I'm writing my master thesis at Siemens. And I've started this thesis topic for 3 months, and also my experience with OAI is also 3 months, so I'm probably the most newbie person in this room, and this is also the purpose of this talk, so to introduce what I'm doing, what I have already, and what we're planning to do in the future. And hopefully you can get the feedback from the experts here so I can bring it back and improve on my research. And I would explain a bit on this very long thesis title. So the motivation of this work is that we all want a reliable, low latency communication, especially in industrial applications. And the thing is that if we only look at the average delay of our packet transmission, we would sometimes ignore that there are extreme cases where the packets takes a long time to arrive, and there are extreme cases if we violate some target delay, then it will actually cause trouble. So the whole idea of this thesis is to come up with a complete analysis to understand and analyze the end-to-end delay of the packet, especially on the cases where they violate the threshold that we defined. So a formal definition here, as you can see on the blue, the green-blue part on the screen, is our definition of a delay violation probability, which means that the probability of the packets with the end-to-end delay that exceeds a certain threshold that we defined. So it depends on the threshold you set. You're trying to make sure that the packets you have the end-to-end delay fallen within the threshold so it doesn't violate anything, and you can have a safe operation in your application. And what we're planning to have in this research composed 3 parts. So first is a theoretical analysis, which we aim to come up with an analytical formula to define our delay violation probability. Or if at the end that doesn't work out, at least we want to try to upper bound it. So at least we know that our end-to-end delay would be fallen within a certain range and then guarantee a safety transmission. And secondly is where so far has been going the most is the experimental measurement. And this is done with OpenAirInterface with some USRPs, which I would give a bit more on how it looks like later. And we introduced the project from KTH called End-to-End Delay Analytics Framework, which is a project that decomposes the end-to-end delay of a packet into several components. And the purpose of it is that so you can see exactly at what phase this packet takes the most time. And third is that we want to use the data that we collected from our testbed. So we have a testbed in Garching, Germany. And we want to use the data we collect here to train a model, so have a machine learning-based prediction. We're planning to train an LSTM and transformer architecture, and then we want to see in different scenarios, can we have a model that can actually predict the DVP of the packets. So this is the whole plan, and currently the theoretical analysis and machine learning based prediction, it's still ongoing, so there won't be a lot covering about it. So mostly would be on the second one, which is what I actually have measured and using the OpenAirInterface. So the whole testbed is done on a DGX Spark, this is connected via the USB 322 USRP B210. And we transmit our signal over the air, so it's wireless. And the G0B, the UE, the core network are all running in a single host, so the DGX Park, basically. And what we do is that we just play around with some different parameters. So for example, we run some tests under different physical distance. We try different resource blocks, and we have some different packet inter-arrival time. So basically, we have a UDP generator, so it just sends some packets under different arrival time. And with different packet size also, so just to see how it changes and how does this DVP varies under different scenarios, and then see how we can use it for later on the model training and the analytical formula. And a bit more focused on this end-to-end delay analytics framework, so I call it ADAF in the following. It's a way that we decompose the packets into different components, and it's just basically inserting some timestamps over the packet's journey in the 5G, in a 5G system, and then later on we use these timestamps to kind of reconstruct how long does it take for the packet to stay in each phase. And it's pretty intuitive in the sense that when you want to measure something, you basically measure the starting point, you measure the ending point, and then you subtract it. Then you get the time it spends in that phase. So take an example is that let's say we want to measure the time that the packet stays in the RLC layer. So the moment it enters, we write a string that is in a ring buffer, and then this string would contain at the beginning a timestamp and then the direction. In our case, we're currently just using uplink, so the U stands for the uplink, and then the place that this packet is going. So as the packet keeps going, you collect more and more timestamps. And now, for example, you can see that you subtract the first one and the third one, then you get the total time that this packet stays in the RLC. And it's basically the same logic throughout the whole protocols. You just do a lot of timestamping like this, and then using these timestamps to do subtractions, and then simply get the time that the packet stays. And there is a data collector thread, which is another thread that goes in a round-robin fashion that collects all these strings into a log, and then later on it's for easier to analyze, and that's it. So another very trivial thing is that if every time we document the time, so the Unix time in our string, what would happen is that it would cause too much burden in this system because you need to check the time every time it's timestamped. So instead, what is done is that every once per second there is a log, which I call it the S logs. This log is the kind of like a table that maps the time counter and the Unix time. And then later on, when we are looking at our log file, we can use this table to reconstruct them by just simply doing linear interpolation, basically. So, for example, if you want a certain, if you are reconstructing a current time point, you find the closest S log between them, and then you just interpolate them, and then you reconstruct the Unix time. And this has the precision of around in the MS level. And the way that this decomposition is done so far is that first, when the packet enters from the IP to the RLC, so when the packet starts entering the RLC queue, it stops. And this is one of the delay component. And then as it leaves the RLC queue, we count another one. So this is when the packet stays in the RLC queue, we just call it RLC queuing delay, so more intuitive. And then the time the packet spends for transmission is also documented. And if the transmission failed, then there will be a retransmission, of course. So this is also documented. And then the time that the packet stays in the physical layer for decoding. and the packet, after it's decoded until it's reassembled again in the RLC layer, is also documented. And then the later one would be from it's reassembled until it leaves. And with this decomposition, what we could get, for example, would be something that looks like this. So you can look at the components basically of how long does this packet stays in each phase. And apparently, like among all of these, there's a very tall bar. So the second one, which is the RLC queuing. So that means that in this packet journey, in this experiment that we have conducted, we found out that the packet spends most of its time in the RLC queuing. And of course, intuitively, the next step that we would do is to plot it out and see how the histogram looks like. So on the left-hand side, you would see is the end-to-end delay of the packet. And on the right graph, you would see is the distribution of the RLC queuing delay. And what is cool and worth noticing is that this has a very similar shape, and also it kind of has this discrete peaks, where it was at the beginning out of my expectation, because I was thinking to expect something that looks more continuous instead of these discrete looking peak. And before just explaining why is it, I think it's good to emphasize that it is because of this flexibility of OAI that we've decided to use, can give us this opportunity to actually dive in and then get the components and most details out of this research. So we can decompose them and then get these graphs and then keeps diving into to see what is happening actually in the 5G system. So back to the DVP, if we get an end-to-end delay that looks like this, we could do is that we could plot it into a graph, so CCDF, a complementary cumulative delay function. So basically from here, you can define your target threshold and plug it into the x-axis, and then on the y-axis, you would have the probability that it's violated. So of course, if you have your target at, for example, 0 ms, then you would see on the graph that it corresponds to probability of 1 because all the packet exceeds this value. And in this graph, you would see those staircase-like looking shape, which comes from the fact that the end-to-end delay is discrete. So of course, when you're increasing your threshold within these non-existing places, there won't be packet arriving. So like the discrete part here on the left graph. So even if you increase it, it stays flat. And this is also explainable from the previous graph. And the next is that, so why does this come from? And we've done several experiments so to see how they interact under different scenarios, and turn out they only change and has this shape when your inter-arrival time is not a multiple of 5. So on the left-hand side of the graph, what you see is a queuing delay distribution of inter-arrival time of 2 milliseconds, while on the right-hand side, the graph is the inter-arrival time of 5 milliseconds. And you can obviously see the difference that on the left one, it's a more continuously distributed, and on the right one, it's more like a discrete peaks-looking shape. The reason behind this is that in our setup, we use a TDD scheme of so different portions of downlink and uplink slots. And the reason behind is that usually between 2 uplink slots, they have around 5 ms of time. So whenever your packet arrives with the inter-arrival time of 5 milliseconds, they always fall into the same place until they get the next uplink grant. And that's basically the reason. So from this, the good thing is that now we can actually explain this graph, and then later on, which hasn't been done yet, using these to try to analytically analyze them and then see if we can actually get a nice formula out of it. So in the future, when we just specify some scenarios, we can get a theoretical distribution of these packets, and then we can skip the time that we do on the actual ground truth measurements, and would be very useful in the applications. So currently, there's not much done, but I think one big takeaway here would be that if we're trying to understand those delays, what would matter is that you actually decompose them and look into each of them so that you would know where is exactly the problem or the things that takes the most. And then accordingly, you can change your parameters or your setup to obtain a better result or to explain everything that was happening behind. And currently, our setup is always just in uplink. We're planning to extend this system also to downlink and also to increase the scenarios to multiple UEs, because right now it's just the simplest form, so one UE and one G-Node B, which would be better if we can have multiple connections, so multiple UEs connected to it. And also what we're trying to do next is to use these data that we collected to train the model, as I was saying at the beginning. So what we're trying to do is to see if they can actually predict the future delays of these packets. And also we want to evaluate how good they predict. So on our test bed, so basically we would compare them with what we actually have. And the key questions that we're hoping to answer would be, for example, how much training data is needed. So if a model wants to learn these behaviors of queuings and transmissions, how hard would it be? Or is it explainable? And the model that will perform better is also interested. And for example, what features would contribute the most? So because in the transmission, there will be, for example, different MCS index, there might be retransmissions, and a lot of different general conditions. So also, we want to know if we turn something on or if we turn it off, we don't use these as the training features, how is it going to look like? And at the end, we want to also see if this can be generalized into some unseen scenarios. So if we, for example, give the model something completely new, like completely different use cases, how well can it predict, and if it can actually give us something nice from it. And at the end, if there is still a little bit of time, we would want to also increase a simulation in NS3 and then see how the NS3 would actually resembles the one in our testbed. And so far, this is everything, but hopefully there will be more. And yeah, I appreciate any feedback from you. And these are our contacts, so also you can write us the mail if you want. Yeah, thank you.
Other questions?
Maybe one remark. I think what you see, in fact, is just that the G-Node B give the opportunity of doing a POOC, so a grant request, yes, every 10 slots or something like that. That's why you have that periodicity of 5 milliseconds. But
yeah, it's the uplink grant, like given by the G-Node B, you mean? Yeah, the thing is, if so usually what happens is that if so on the left one, because the time that it arrives, like every time when it arrives, it has a different time until it gets the uplink grant in the left graph. So that's just cause why it is more like a continuous shape. But the one on the right hand side is kind of because every time when it arrives, it comes in a multiple of 5, which in our scenario is the distance between continuous uplink grants. So that causes the reason that when it arrives until its next transmission, they always wait for the same amount of time. And yeah, because I think in the current setup, it's like a dynamic grant scenario. And I was also hoping if there's possible to try to change it to like a configured grant and then see like how would it behave differently and stuff. Yeah, I hope this.
Maybe just one small question. I mean, the measurement, like the tracing points, you implemented them yourself, or did you leverage some work that exists?
Yeah. So it's It's a project from the KTH, as I was mentioned at the beginning. The only difference is that we just implemented it on the DGX Spark, so we move it onto the Spark system. And yeah, because it also comes with a lot of nice feature in the Sionna research kit, so maybe later on we also want to try something new there, so the neural receiver and stuff.
Okay, maybe just the one thing, and that goes also a little bit in the direction of what Sarah said before, because there was already like attempts of making like a more or less generic tracing mechanism to measure these delays, which is called LATSEC. And I think that was also presented, so maybe that builds on top of it. I was reminded by these traces because I think they look similar.
This is based on.
Ah, okay, all right, okay.
It's based on.
Okay, thank you.
Thank you.
Okay, thank you.